Now force between two parallel currents. Two parallel currents. So let's take two parallel current carrying wires. This is the first one, and this is the second one. So let's say current is going in this direction in both the loops. This is I1, this is I2. Now according to Coulomb's law, force on both the charges due to each other is given by F is equal to K Q1 Q2 upon R. So like this way, what would be the magnetic force applied by each of these wire on other one? Okay. So due to this I1, magnetic field would be in outward direction this way. Okay, perpendicular to the current, and due to this same way. Okay, current is going in this direction. So this will apply force. This is the conductor 1, this is the conductor 2. So force would be F12 due to this one, and due to this conductor it would be F21, right? Let's say the distance between these two wires is R. So first of all, the magnetic field due to this wire can be given as B1 is mu 0 I1 upon 2 pi R. Remember the formula, magnetic field due to a wire is given by mu naught I1 upon 2 pi R, right? And similarly, yes, sir, magnetic field due to this wire would be what? Same, mu naught I2 upon 2 pi R, right? So force between them is given by what? I2 in the bracket L cross B. We have just derived this formula, right? And it can be given by I2 LB sin theta. And if the theta is 90 degree, it is simply I2 LB. Here it is B1 because we are finding F21. Okay. So I2L, and what is B1? It is mu naught I1 upon 2 pi R. So the force can be given as mu naught I1 I2L upon 2 pi R. Same as Coulomb force, as you can see. Here it is Q1 Q2, here it is I1 I2. Here it is constant K, here it is constant mu naught upon 2. Okay, write it down. Torque on current loop for magnetic dipole. So let's take one current loop. Okay, so let's talk about an electric motor. So this electric motor, these are the two magnets. Okay, and there is this loop right here, and let's say current is flowing from this end to this end, right? So here you can notice, here the direction of current is in this direction, and here it is in opposite direction, right? Now because of ns there is this external magnetic field, right? And let's say the side, the length between these two ends is a, or we can say separation between these two magnets is a, and this length is b. Okay, length of the loop is b. So let me draw this loop separately. Okay, So this is our loop. Current is going in this direction. Now because of the external magnetic field would be from N to S or S to N? N to S, right? So this magnetic field will act on this section in upward direction. It will apply force on this section in upward direction, right? And on this section it will apply force in downward direction. Because of these couple forces, this loop will rotate. We know that this length is A, so this is A by 2, this is A by 2. And what is this magnetic force? Magnetic force is nothing but I in the bracket L cross B, right? And here length is what? It is A by 2 cross B. It is simply I A by 2 into B, or what? Do we take A by 2 or this length B? Tell me. We will take this length B, length of the loop. Okay? Because we know that here the current is going in this direction, right? Length is B. The force was given as ILB. What is the length? It is B. External magnetic field is B, so we can write it as ILB. Okay, so force would be IBB. And here it is also IBB. So they are making a force, couple force, right? This is A by 2 distance, this is A by 2 distance. One force is in upward direction and one force is in downward direction. So according to rotational motion, if there are two couple forces, the system will rotate, and due to this rotation, who will cause the rotation? These forces, right?
Yes, sir.
Torque is given by what? R cross F.
F cross R.
Or R cross F. So what is the perpendicular distance? It is A by 2 into F for both the cases, which is simply A into F. This is the total torque acting on the system. And what was the force? It was IBL, right? IBB. Can we write it this way? I in the bracket AB into B. Yes or no?
Yes.
And what is this AB? AB is nothing but the area, right? This is A is length and B is right. So AB is nothing but area. So we can write it as IA into B, right?
IA. Yes.
And there comes this concept of magnetic moment. Magnetic moment is given by current into area. Okay, like in electrostatic we have defined magnetic dipole, and it was what? Q into 2A. So like this way in magnetostatic there is this magnetic moment, and it is given by IA. So we can simply write it as M into B. Okay, and if there was this original expression, it was what? Sin theta, right?
Yes.
So if you write it this way,
it will become M cross.
It will become M cross B. So this is the torque acting on a current loop. Okay. So this was our core purpose, finding the torque on a current loop.